This is the seismic loading presentation. Hazard is one of the three components of risk. Part of the advanced preparation for a risk assessment is developing the seismic loading information in Chapter 5 of an SQRA report. The primary questions to be answered in Chapter 5 are, what is the hazard and what drives it? This presentation presents an overview of the seismic loading for SQRA. Here's the outline for the presentation. Seismic sources will be discussed as they provide the necessary background for the source of the hazards that drive the loading curves. The primary products of Chapter 5 are the seismic hazard or loading curves, and two RMC toolboxes are used to develop the curves. Moving beyond the seismic hazard, design earthquakes and critical loading considerations for all potential failure modes will be discussed. Seismic sources. The seismotectonic setting and seismic source zones inform what drives the hazard. Attenuation of ground motion differs between the central and eastern United States and the western United States because the rock found in the western United States is softer and more fractured than the rock in the central and eastern United States. The boundary between these regions is located along the eastern edge of the Basin and Range Province, a vast physiographic region covering much of the inland western United States and northwestern Mexico, characterized by abrupt changes in elevation, alternating between narrow, faulted mountain chains and flat, arid valleys or basins, as a result of tectonic extension that began around 17 million years ago. In the central and eastern United States, a significant contributor to the hazard is often the regional aerial source zones that generate the historical background seismicity. In other words, fault sources are rare and generally surrounded by large aerial source zones. In the western United States, the fault sources are usually better known and are conceptually surrounded by the background in between sources. In many locations, particularly in the western United States, multiple individual seismic sources, as well as aerial sources, for example, background seismicity, contribute substantially to the total seismic hazard. Deaggregation plots can provide useful information on the relative contribution of different seismic sources to the annual frequency of exceedance of specific ground motions in terms of magnitude and distance. These seismic sources will produce different ground motion frequencies and time histories, which could affect various structures differently. The USGS Unified Hazard Tool is generally used to obtain the deaggregation information. As of April 2022, it only contains the 2014 Coterminous United States long-term data set, whereas the latest data set is from 2018. Significant differences are not expected. Increases in seismicity in the central and eastern United States have been documented since about 2009. Most of the human-induced earthquake activity in the central and eastern United States is caused by injection of wastewater or other fluids into deep disposal wells that cause pressure changes that can weaken a fault and therefore bring it closer to failure. Induced earthquakes generally occur within 5 to 20 kilometers of an injection point. The seismic hazard may be higher in these areas of potentially induced seismicity than the hazard depicted on the National Seismic Hazard Maps. Assessing the hazard is difficult because induced seismicity can vary rapidly in time and space based on changes in wastewater injection, which can be caused by economic or policy decisions. Seismic hazard curves. Absent a recent site-specific PSHA, USACE risk assessments utilize the USGS regional PSHA. This table summarizes the available USGS seismic hazard data sets. The gridded values in these data sets are imported into the RMC Seismic Hazard Curves Toolbox to generate the loading curves for PGA and other spectral accelerations of interest. As of March 2021, the USGS Unified Hazard Tool only contains the 2014 CONUS long-term data set. Once the Unified Hazard Tool is updated with the 2018 data set, the toolbox will be updated because the Unified Hazard Tool will dynamically update the data set from published gridded values. Therefore, the gridded values of the 2018 CONUS long-term data set must be downloaded and imported into the Toolbox. These three data sets are for the CONUS short-term data set for induced seismicity. These are the available OCONUS long-term data sets. The data sets bounded by this red box are considered legacy data sets by the USGS. This table summarizes the available USGS data sets by ground motion. CONUS long-term for both the Western United States and Central and Eastern United States data sets are available for 8 site classes, whereas CONUS short-term induced seismicity and legacy OCONUS long-term data sets are only available for site class BC. To obtain the seismic hazard curve for other site classes, ASCE 7 is used, which is discussed later in this presentation. 4 urban regions in the Western United States have been identified where enhanced shaking is likely to occur due to deeper basins resulting in larger, long-period ground motions. Therefore, 4 additional data sets are provided in the 2018 CONUS long-term data set. Use them if your site is located in one of these areas because it makes a difference. Soil deposits amplify the level of ground shaking relative to the level of shaking in bedrock. Site class is a simplified method for characterizing the ground motion amplifying effects during an earthquake by evaluating the relationship between the average shear wave velocity in the upper 100 feet of the soil rock column and the amplification of shaking at the ground surface. Shear waves are the earthquake waves that generate the strongest horizontal shaking and are the most damaging to structures. Soft soils with lower shear wave velocities generally produce greater amplification than stiff soils with higher shear wave velocities. Site class A represents a hard rock condition, generally east of the Rocky Mountains, and site class B represents a soft rock condition typical of competent rock sites on the West Coast, where earthquake shaking is neither amplified or reduced by the near-surface geology. Site classes C, D, and E represent increasingly softer soil conditions, which result in a progressively increasing in amplification of ground shaking. Site class F is reserved for unusual soil conditions, where prediction of the amplification of earthquake shaking can only be determined by a site-specific evaluation. As mentioned previously, CONUS long-term data sets are available for 8 site classes for the Western United States and Central and Eastern United States, whereas CONUS short-term induced seismicity and legacy OCONUS long-term data sets are only available for site class BC. For those sites, ASCE 7 is used to modify ground motions for peak ground acceleration, short period 0.2 second spectral acceleration, and long period 1 second spectral acceleration for site class effects as shown on this slide. The seismic hazard curves are the primary product needed for seismic loading and are obtained from the RMC Seismic Hazard Curves Toolbox. Using the Toolbox, plot the mean hazard curve from the appropriate USGS dataset or datasets and any site-specific PSHA if available. Most USACE projects do not have a site-specific PSHA unless in a high seismic zone. For most potential failure modes, the mean hazard curve is appropriate. However, the hazard curve for the specific seismic source may be needed for some potential failure modes. For example, concentrated leak erosion due to fault rupture beneath the dam footprint. Most geotechnical potential failure modes will use the mean hazard curve for PGA. For structural potential failure modes, other spectral accelerations of interest may be needed. Absent a site-specific PSHA, the USGS is the primary source of seismic loading information for most USACE risk assessments. USGS data is better suited for more frequent, small to moderate earthquakes, but is much less reliable for infrequent and very large events associated with design and evaluation of high-hazard dams. The USGS includes PGA values greater than 2G in AEP values as low as 1 times 10 to the minus 7, or 1 in 10 million, which implies these unrealistic accelerations can occur. And very large PGA values grossly overestimate real-world seismic source limited accelerations. The Toolbox limits plots to PGA less than 1 G for the central and eastern United States and less than 1.5 G for the western United States, and AEP more frequent than 1 in 100,000. Extrapolation to remote AEP less than 1 in 10,000 is shown as a dashed line due to the considerable uncertainty. Here's an example of a site-specific hazard curve for the peak ground acceleration. The mean hazard is shown as a solid line, and the median or 50th percentile is shown as a dashed line. Confidence intervals are also shown. The USGS seismic hazard curves are currently limited to only the mean. This example illustrates the large uncertainty associated with ground motion predictions less frequent than about 1 in 1,000 AEP. The USGS issued one-year forecasts in 2016, 2017, and 2018 based on the previous 2 years of seismicity, in other words, the CONUS short-term data sets. The RMC has prepared a list of dams potentially affected by induced earthquakes. If induced seismicity applies, include the mean hazard curve with and without induced seismicity. Although the model is a one-year forecast, it seems reasonable to assume a similar forecast applies to slightly longer time periods, in other words, before the next periodic assessment in 10 years, if recent earthquake rates remain unchanged. Therefore, the curve is shown as a solid line for AEP greater than 1 in 10. Since there is a significant amount of uncertainty, the curve is shown as a dashed line for AEP between 1 in 10 and 1 in 200, where it is arbitrarily truncated. Short-term results must not be applied for very low AEP because hazard estimates from induced earthquakes are not compatible with estimates of long-term seismic hazard caused by tectonic processes. The RMC Seismic Suite. The RMC Seismic Suite contains 2 toolboxes to assist in developing the seismic loading: the RMC Site Classification Toolbox and the RMC Seismic Hazard Curves Toolbox. Both toolboxes are located in the Periodic Assessment folder on ProjectWise under CDALs, which is also known as the Facilitator's Briefcase. The RMC Site Classification Toolbox can be used to help estimate the site class. A common mistake is not assessing a 100-foot profile because of rock or lack of site-specific data. If the site profile is terminated shallower than 100 feet and the underlying rock layers are not included, a less favorable and unrealistic site classification will be obtained. Judgment may be needed to extend the profile where the depth of the geotechnical investigation does not extend to 100 feet. The RMC Seismic Hazard Curves Toolbox post-processes imported USGS data sets and applies the site class if applicable. This toolbox generates the report-ready seismic hazard curves. Here are some takeaways for seismic hazard curves as a preparer of Chapter 5, Facilitator, QC Reviewer, or ATR team member. Were the site class and seismic hazard curve toolbox worksheets provided in the appendix and checked? Is the site class appropriate for the foundation conditions? If the site class differs significantly by project feature, were additional site classes and hazard curves provided? Were other appropriate spectral accelerations provided based on the project features and potential failure modes? Was the most recent USGS hazard curve used? Does the USGS hazard curve consist of 2 data series, a solid line for an AEP greater than 1 in 10,000 and a dashed line for an AEP less than 1 in 10,000? Was a hazard curve for induced seismicity plotted but not applicable? If a site-specific PSHA is available, was it plotted with the USGS hazard curve? If a DSHA is available, is the vertical reference line for the MCE plotted? Critical loading considerations. Safety assessments using design earthquakes may inform the critical loading. Two primary design earthquakes are the operating basis earthquake, or OBE, and the maximum design earthquake, or MDE. The OBE has an AEP of 1 in 145 and is obtained from a probabilistic seismic hazard analysis, or PSHA, and can reasonably be expected to occur within the service life. The project functions with little or no damage and without interruption of service. Often this ground motion is very small and unconservative for the intended purpose. Usgs is proposing 1 in 475 AEP in ER 1110-2-1806, which is already used by the Australian Committee on Large Dams, or ANCODE, and the liquefied natural gas industry. The MDE depends on the criticality of the project feature being evaluated. Critical features have life loss potential, which is informed by a risk assessment or hazard potential classification. For normal features, the MDE has an AEP of 1 in 950 and is determined from a PSHA. The project performs without loss of life or catastrophic failure, although severe damage or economic loss may be tolerated. Many hydraulic steel structures, for example spillway gates, were designed as normal structures but are now considered critical features. For critical features, the MDE is the maximum credible earthquake, or MCE, which is determined from a deterministic seismic hazard analysis, or DSHA. It is the largest earthquake that can reasonably be expected to be generated by a specific source on the basis of seismological or geological evidence. It is typically associated with ground motions between the 50th or median and 84th percentiles, or median plus 1 standard deviation, or a higher percentile. Critical loading for dams is an earthquake with an AEP that is likely to result in breach based on thresholds from existing seismic evaluations or other information. If the failure threshold is unknown, the MCE and its AEP from a site-specific DSHA and PSHA are used. Often, a site-specific DSHA and PSHA are not available. If there are no obvious earthquakes, for example, no active faults are identified, or thresholds from existing evaluations, the ground motions are typically linked to a long return period, for example 10,000 years. Although this may be conservative, it is considered adequate for SQRA to identify seismic potential failure modes that warrant closer examination during an issue evaluation study. Historically, most levees have not been designed or evaluated for seismic loading. However, levees have been damaged during earthquakes. If the peak horizontal ground acceleration is less than 0.1 g at free field conditions for the OBE, seismic potential failure modes are non-risk drivers. The threshold is lowered to 0.05 g for very loose to loose soils. If the OBE's PGA is greater than 0.1 g, the loading frequency must be considered. A frequently loaded levee or floodwall experiences a water surface elevation of 1 foot or higher above the elevation of the landside levee or floodwall toe at least once a day for more than 36 days, or 10% of the time, per year on average. Frequently loaded levees and floodwalls should be designed for seismic loading to maintain the integrity of the levee or floodwall and its internal structures without significant deformation or vulnerability to internal erosion. Therefore, the critical loading for levees is the OBE with 1 in 475 AEP. Seismic-initiated potential failure modes are generally non-risk drivers for levees and floodwalls that are intermittently loaded due to the lack of water above the landside toe for a significant period of time, and if damage were to occur, interim repairs could be performed to restore some intermediate level of protection. If interim repairs cannot be completed prior to a subsequent flood, or the subsequent flood is forecasted to exceed the compromised or intermediate level of protection, the leveed area would likely be evacuated. For all levees and floodwalls that exceed the minimum ground motion threshold, a seismic vulnerability evaluation will be performed if reasonably addressed within the scope of the SQRA. A seismic vulnerability evaluation is performed to estimate the scale and location of areas of potential seismic damage that need to be addressed in a post-earthquake inspection and remediation plan. The OBE is recommended as a starting point. a range of earthquakes with AEP significantly less than the OBE, up to breach, based on thresholds from seismic evaluations or other information, or the MCE, whichever occurs first. If the MCE is not available, use an earthquake with 1 in 10,000 AEP from a PSHA. The findings of the evaluation are documented as a major finding and understanding in Chapter 1, as well as in the appendix. The coincident hydraulic loading represents a relatively high but normal hydraulic loading which can be expected to occur every year. It has a 10% annual duration exceedance and is expected to be at or above 36 days, or 10% of the time per year on average. The hydraulic loading can be based on either a 10% annual duration exceedance for a headwater level, or a 10% annual duration exceedance for a differential hydraulic head between a headwater and tailwater level, whichever results in the largest hydraulic loading on the structure. The water levels to assess coincident hydraulic loading are obtained from a stage duration relationship. While other stage duration curves for partial series may be provided, the annual series for coincident water level is used. The example on the left is typical for a flood risk management dam, and the example on the right is for a run-of-river navigation dam. For dam consequences, the normal high pool or NHP scenario is typically used, which has the same annual duration exceedance as the coincident hydraulic loading definition on the previous slide. For levee consequences, the modeled scenarios are based on a percentage of the levee height, not an annual duration exceedance. Therefore, select the scenario that best approximates the 10% annual duration exceedance. When evaluating subsequent flood events, consider the compromised or interim level of protection following the earthquake. In all cases, teams must consider how the warning and evacuation for seismic potential failure modes could be different than the modeled flood scenario.
This concludes this presentation.